All right, we are in Windows World again, Building 26 with Mark.
Charles, hey.
Everybody knows you.
Hey,
Introduce yourself, man.
Mark Russinovich. I'm a technical fellow in the Core OS division, working on Windows 7 and working on future versions of Windows.
Excellent. So we're releasing the M3 build, as it's called, at PDC. And so I wanted to come today and talk to you about sort of, from an operating system perspective, what's new? What have you guys, what's the evolution of Windows look like in this snapshot?
Yeah. So, well, one of the things that we've been saying publicly leading up to now is that it's really built on the Vista code base. There's no major changes. We've really concerned about maintaining application compatibility. I mean, that's one thing that we learned a big lesson on in Vista is if you're going to break it, it better be for a really, really good reason.
Yeah.
And we haven't found really, really good reasons, at least not to break it on any kind of scale that is going to impact people. So, but that said, there are a whole bunch of improvements all over the place in kind of the system, which is what I typically talk about, Windows internals.
Excellent.
Level.
Let's do it.
All right. So
just to be clear, though, I want to get this out there. I mean, a lot of the innovations that were in Vista, and we had that conversation with you, I guess, a couple of years ago now, about what's new in Vista. Those were actually pretty substantial and interesting, and you built on top of it. So my point is, those weren't a failure. Just to get that right out.
Yeah.
Okay, that was an interesting innovations you guys have done. Now you built on top of it. So what exactly have you guys done?
So I've got a whole laundry list of things, and some of them are kind of related to each other, and some of them aren't. And so I don't want to start and imply that by mentioning one first or last that there's some kind of prioritization or something's more valuable than something else. But one of the things that I think is really cool is a really big in the sense that it has been something that as systems have gotten bigger and we've got more cores, was rearing its head as a problem more and more, and it was a daunting engineering exercise to figure out how to address this problem, and that is something called the dispatcher lock.
Okay.
So in the scheduler leading up to Win 7, whenever a thread waits on an object or wakes up on an object, whenever it makes a transition like that from running to waiting in the scheduler, there's an acquisition of a global lock called the dispatcher lock. And so if you've got a multiprocessor workload where you've got lots of threads running on the system on different CPUs and they're waking up and sleeping and communicating with each other, the dispatcher lock becomes what we call the hottest lock in the system, which is that lots of threads, lots of CPUs end up spinning waiting for that lock, and you end up not being able to do anything useful while those threads are spinning. And in a 2-way or 4-way system, or even an 8-way or 16-way, that's not a big deal, but as you get into larger and larger systems, it gets into a bigger and bigger problem. And when you start looking at SQL workloads, which is what we see today on larger systems, it ends up being a significant issue for limiting the scalability of those systems. And one of the things that we're doing is looking forward to, we're seeing, of course, Moore's law, where heat and power and density not being able to support the kinds of increases in clock speed that we've been seeing, and now we're moving to multi-core systems, and there's people that say we're going to have 128-way systems on our desktop in a few years. In any case, so it's a big problem on servers as they get bigger. It's also potentially a problem in the future on client systems. And a guy named Arun Kishan, who's a kernel developer here, kind of a superstar, took it as a kind of a side project to see if he could break it. And Dave Cutler, the original architect of the scheduler, spent a lot of time himself working on trying to get rid of that dispatcher lock. And kind of he moved on to the Red Dog team, which is something also that's been disclosed at the PDC. So Arun took over the scheduler and decided to tackle it himself, and it's one of those cases, I think, where somebody come in with a fresh look from the outside and they're not involved with the original development of the code, can see the problem in a slightly different way and figure out a way through it, and he did that.
Outstanding.
And so that's kind of an unexpected bonus. We couldn't go in planning to get rid of that because it was such an intricate problem, but he managed to do it.
So let's talk a little bit about at a high level. How did he solve the problem? He broke it up into pieces. The
way he addressed the problem was to look at the way that the scheduler acquires locks down through all its code paths with timers, with asynchronous procedure calls in the normal wake up and wait, and identified requirements for each one of those. If you were going to get rid of the dispatcher lock, how did things have to operate? And started analyzing it bit by bit that way, and then had a kind of a fundamental realization that he could get rid of the lock by introducing another state in the way the scheduler operates. Instead of just I'm either running or waiting, now there's two states. There's a pre-waiting and then I'm really waiting. So in the pre-waiting state, he got rid of the global lock, and introduced lock for each object. So normally when a thread is synchronizing, it's waiting on some kind of object, like an event or a mutex or another process, and waiting for it to become signaled or ready to tell the thread it's ready to execute. And like I said in the past, it would, when it went to check the state of that object to see if it was signaled or not, would grab the dispatcher lock, and that would protect changes to that object happening while it was looking at that object to see if it was signaled or not. So he introduced the second state, this pre-wait state, where he grabs the lock on just that object, no dispatcher lock, no global dispatcher lock, and now that object is protected from changes. But changes can be taking place for other objects that this thread isn't interested in, and that's where you get the scalability, because now you've got threads on different processors looking at different objects, not necessarily the saved object, and you don't have everybody artificially waiting on something that's not related to what they're really interested in.
Sure, and I mean, obviously, as you already mentioned, SQL Server, but in the server context of Windows 7,
yeah,
this makes perfect sense.
It's awesome.
Yeah.
And the thing is, that's related to kind of another change, which is big, which is that customers have been coming to us, even since I've been here at Microsoft, from large enterprises saying, hey, we want to run on greater than 64-way systems. What do you got for us? And we've had nothing. The way that NT was originally designed, Dave Cutler basically designed the scheduler looking far into the future for the time he was designing it, and basically said, okay, for 32-bit systems, what originally NT was written for, back then it was very rare to have a multiprocessor system, and so he imagined that by the time we'd end up having 32-way systems, it'd be a long runway. But for performance, the scheduler uses bit masks, or used bit masks, of the word length for the CPU. So on a 32-way system, in a 32-bit system, he used 32-bit word to represent the state of each processor, where one bit represents things like whether the processor's idle or not, and the affinity mask for threads, which says which of the CPUs it can run on, represented by bits. And that made it very efficient to do tests like, are there any idle processors? What's the highest numbered non-idle processor for making a scheduling decision? And other operations like that. On a 64-bit system, the word is 64 bits. And so, just by extension, 64-bit Windows supported 64 CPUs, logical processors. So, now 64-way systems, again, one with many core and larger machines, we see that becoming a limit. So, again, making Windows look out for the future, because what's the high end today is going to end up moving down over time.
Yeah.
We got rid of that. So now there's support for up to 256 CPUs now in Windows 7.
Nice.
And the way that was accomplished is to have logical processor groups. So a thread is always within a group of processors, and the group of processors can have up to 64 on a 64-way system, and that's 64 ways where this is really enabled.
Amazing.
And so
that's great.
So we did by doing the groups, though, that made the existing APIs basically work, because the existing APIs take in bit masks, and so now if you call set thread affinity using the legacy APIs and you say I want to be on these processors and you identify the bits, well, you're really saying I want to be on these CPUs for the processor group that my thread is in. And by default, all threads that don't specify processor group are in processor group 0, which are all the same. So programs that are written to expect, hey, I'm on a 32-way system or 64-way system, and when I'm setting affinity and so on, I expect to be within, operating within the same set of CPUs that all my threads, they'll continue to work.
Excellent. So this is sort of the beginning of Windows being ready for many-core.
Right. Ready for many-core and already ready for really high-end workloads. That's
awesome. So what else? What else is going on?
So let's see some other things. Landy
Wang.
Landy Wang,
Memory
who's
man.
next door, memory manager architect. He once Arun got rid of the dispatcher lock, that showed up, that made the second set of hot locks appear, in performance workloads, and now that it wasn't gating or performance or gating scalability. And one of the locks that started showing up in some workloads is the PFN database lock. So the PFN database is a list representing each physical page of memory. And the memory manager, when it's assigning pages to process working sets, would go and lock that entire array and then make the assignment. You move the page onto a list saying it belongs to that process, and then unlock it. And so that also becomes a global lock there. And so Arun's work inspired Landy to go and do a tremendous effort to go and get rid of that lock as well. And so he had to go fix, I don't know how many hundreds of places throughout the system where previously it would acquire the PFN lock, and then he broke it down into finer grain locks.
Amazing.
And so now we got rid of that one too. And of course now there's another set of locks behind that one, but now that opens the door for even more scalability. So there's cases where processes are allocating or releasing virtual memory and getting working sets moved in, and working set pages moved into and out of them that now don't have that bottleneck on a PFN lock.
Excellent. Now let's just out of curiosity, I mean, for the average user like me, right, who's using the desktop flavor of Windows 7 for the most part, and I'm going to be running definitely on 2 cores because you can't buy a 1-core system anymore.
Yeah.
What does this mean for me? What does this mean for us?
Not
performance.
Okay. It actually doesn't do a whole lot for the small systems like that.
Okay.
Probably negligible.
Negligible.
Yeah. As you start to get up to 32-way systems and 64 and higher, then those things start to show up.
Now, does it add sort of the capability for application developers to, build applications with more muscle?
Yeah, I mean, one of the things that we're recognizing, the whole industry is recognizing, is we need to make use of these cores that are coming down, and the OS can't get in the application's way.
Absolutely.
Right. And one of the other changes kind of related in this space is the user mode scheduling feature that's gone into Win 7. And this is, user mode scheduling addresses the problem where applications want to control their own schedules. They want to do lightweight scheduling of their own scheduling entities, not really threads, because that's a kernel construct.
Okay. And
what that gives them is that instead of being preempted by the kernel scheduler, they make very quick transitions. They know when a thread, one of their scheduling entities, is about to go to sleep or about to wait on some piece of work being done, and that thread simply calls into their user mode scheduling loop, and that user mode scheduling loop says, okay, this scheduling entity can't do any more work, so I need to find the next guy that is ready to do more work, and he just ends up calling that guy's function.
Okay.
And so basically it's like just sitting in a loop up in user mode, just going from one logical work task to another without the kernel getting involved. And SQL Server, for example, used when they published TPC results, would run SQL in what's called fiber mode, where the SQL workloads execute using fibers up in user mode, which are these lightweight threads. The kernel knows nothing about fibers. And that's fine if you spend all your time in user mode and never call into the kernel. But if you call into the kernel from a fiber, the problem is that fibers can switch threads and kernel threads. And if a fiber started life on one thread and executed some call, and that the kernel needed to do some processing for that system call, typically would go back to that same thread, or reference state associated with that thread. And the problem is that fiber might now be on another kernel thread running on that, and so there's a kind of torn state problem.
Sure.
So with user mode scheduling now, there's support for running a user mode scheduler, not using fibers but using the UMS services, so that your work items, your work threads up in user mode, now when they make a transition into kernel mode, they get connected back to their thread that they're associated with. So you make a system call, you get connected back to your thread, you come back, that system call finishes, you come back up in user mode, you go back into the user mode scheduler, and then you go do another work item. And if you end up back on that same work item that's associated, bound to that kernel mode thread, and you make another system call, you just go right into kernel mode because you don't need to make a switch. If you go back out and then switch to another work item that's associated with a different kernel thread and make a system call, as you enter kernel mode, the scheduler goes, oh, you're on the wrong kernel mode thread, let me switch you, and it does a fast context switch over to that other kernel mode thread, and your aligned user mode and kernel mode are connected in the right way.
Excellent.
And so that can potentially give SQL an opportunity to, well, let me back up and say what the reason that people don't in production run SQL Server in fiber mode is because they've got their own code running up in SQL, and that code makes calls, system calls, makes Win32 calls, and of course on fibers that's problematic. So which means that fiber mode is really only, like, you're not running any of your own code and you want to get a great benchmark number. So with user mode scheduling now, that will enable SQL to take advantage, to get the benefits of fiber performance and yet get the correctness of when interacting with Win32.
Excellent. I mean, what about for, say, other applications, though? Like,
Yeah, as another example of somebody that's going to use this is the concert runtime, the concurrent runtime group. And they're looking at this, enabling this mechanism so that on Win7 systems they can take advantage of the UMS to get great performance for their scheduling. And nobody's going to be, the idea is that we don't expect people to be using the UMS scheduler APIs themselves, but rather if they want to write an application that wants that benefit of scheduling code in user mode, they'll be using the concert runtime instead.
excellent. And so when we talked a lot about in these conversations about the user mode kernel boundary, and it's safer to screw up in user mode than in kernel mode.
Yeah.
This gives you sort of a similar sort of analogy, but you're not going to screw up the thread synchronization, down in kernel mode with what you're trying to do up in user land.
Right.
And so your data will make sense and you're not
Exactly.
corruption, and you leave the user like, what's going on.
Yeah.
So it sounds like you've done a lot of work, and I know Sanofsky's talked about this on the E7 blog.
Uh-huh.
A lot of work with performance, the basic things that a general purpose operating system needs to excel at.
Yeah.
Performance, reliability, stability. So clearly you guys have done a lot of work in the performance area, and scalability.
Yeah.
Reliability as well, right? I mean, this is going to help reliability. Are there any specific things you've done for, you don't have to reboot Windows 7 as much as we do Vista? Of course, I haven't had to reboot Vista very much to solve problems,
Yeah.
by the way, just so you know,
Yeah.
which I've been impressed with myself. But what have you done in that area?
In that case, there's nothing major, and there's a lot of fit and finish, a lot of going after, like the E7 blog talks about, we've analyzed the boot process up and down. We've got something called, I can't remember what we're calling it internally, fast boot, which is parallelizing plug and play during the boot process so that plug and play can occur in parallel for different parts of the device tree.
Nice.
And plug and play is a matter of asking buses what's on your bus and then starting the drivers for those devices that are that have been identified, and kind of a recursive process that builds up the plug and play tree. That's been parallelized. Also, there's been more work on prefetching things and overlapping the CPU with I/O and doing that in a more intelligent way. We had Ready Boot in Vista, which, if you want to see an example of something that's has a drastic impact on performance, go turn off the Ready Boot service, because Ready Boot's also part of that service. And you'll lose that boot optimization, and it should be pretty obvious that you've lost it.
Yeah.
And what Ready Boot does is learn over multiple boots. So there's been more work in that area as well. Related to performance, though, is battery life, and being designed for laptops is
Great.
important. And so one of the things, there's a couple things there that have been done by the kernel team to to fundamentally improve battery life. One of them is called core parking, and core parking is a recognition that a lot of the times our systems are idle, and if not all the CPUs, at least some of the CPUs are lightly loaded, and maybe we could take all the kind of background processing that might go across your four-way desktop system and put it all on one CPU and let those other CPUs go to sleep. And so the core parking algorithms in Windows now influence the scheduler, where it will say, and based on power and load, if we've got underutilized, we're running at 10% on each CPU on a four-way, well, let's put that on one CPU, let those other CPUs go to sleep.
Excellent. And
they can go into deep sleeps then if we're not waking them up. And in technology from Intel, the Nehalem processors actually let entire sockets go into very deep sleep. So the core parking algorithms are also aware of the topologies and knowing that it's not good enough. We get some benefit from putting one core on a socket that might have two cores on it to sleep, but we get even more drastic benefit if we put both of those cores to sleep, because that lets the whole socket go to sleep. Excellent. So that's some of the work in the core parking space. And related to that is we don't want to wake up CPUs either once they've gone to sleep. And one of the problems that we get on Windows is there's lots of timers firing for lots of different reasons. The network adapters drivers got a timer firing to check things, and some other things doing a periodic thing, schedule a timer. And one of the problems that we've seen is that you get all these timers and they're not perfectly, the timers are really, hey, just wake me up at this period. Mm-hmm. They're not asking to be woken up on a period aligned with some time interval. In other words, I want you to wake me up every 10 seconds or every 5 seconds or every 500 milliseconds, but I don't care if it's exactly at the hour and starting there. It can be offset from that. That's fine, just as long as you're calling me in a regular way. And when somebody schedules a timer prior to Win 7 or prior to using the timer coalescing APIs, where you can say, I don't care that you don't call me right away and then continue this period, you get all these guys scheduling timers and they all end up being offset from each other. So somebody can say, wake me up every 7.5 milliseconds, and somebody else says, wake me up every 15 milliseconds, and you look at that and you say, well, if you looked at those two timer patterns, we should really just be waking up every 7.5 milliseconds, and then calling both of those guys, because one guy will wake up will call every other time, mm-hmm. and the other guy will call every time. But if those guys prior to Win 7 end up registering their timers as slightly offset from each other, then we end up waking up every 2 or 3 milliseconds, to wake those guys up. They're offset, so we're waking up more often than we need to. Mm-hmm. So timer coalescing API says, I don't care, just wake me up at this regular period, and I don't care when you start. And then what we do is align these guys so that we're waking up the system less frequently, which lets the CPUs go into deeper sleep states.
Perfect. Which, of course, this is the age of where green computing really matters.
Yeah. Yeah.
And this is like explicit, low-level, innovation that's helping.
Yeah. And so we've gone and gone through a bunch of the drivers in the system, the core subsystems, and change them to use the timer coalescing APIs.
So you use the D word, and I think one would argue that if Vista had one, sort of, I wouldn't say Achilles heel, but certainly from a perception standpoint, were the drivers, and the fact that people didn't have drivers ready when Vista shipped. But not only that, but when we shipped Vista, we broke drivers that already existed, because we made like really severe changes in the security model. Yeah. For one example. Yeah. So let's talk a little bit about, in Windows 7, you're a technical fellow, you had to think about this stuff. What did you come up with to maybe when we release Windows 7 to not all of a sudden have a lot of broken devices out there?
So in all cases, we work with existing Vista devices, device drivers. So there have been some changes to drivers like in the printer space and the graphic space. So there's DX11 now in Win 7, and so you've got to have a DX11 driver to take advantage of the DX11 features that will run with your Vista WD driver. on Win 7.
Perfect.
So it's not like you're dead in the water, you're going to get crappy performance or whatever, you're going to get great performance. Like I said, we learned that lesson.
I know.
Yeah.
Now, for driver writers specifically, because I think if you look at the sort of the topology of developers who actually write things that install on Windows, a lot of them are driver developers, right? A lot of, anyway, that seems to be the case. Have we done anything specifically to, say, enhance or evolve the kernel mode driver framework, the user mode driver framework, to actually make the composition of drivers in Windows, maybe easier and safer?
So we've every release, starting a few releases ago, the kernel mode driver framework, takes out a lot of the burden of doing the grunt work out of writing a driver. And so if people are writing a driver that fits into the kernel mode driver framework, which most drivers do, then you're foolish not to be leveraging that. Also, there's user mode drivers, which a lot of people aren't necessarily familiar with. User mode drivers allow you to, for a bunch of different device classes like USB and HID and things, to move those drivers up into user mode. And now if you get a failure in that driver, then you crash the driver hosting process, it restarts, and the user doesn't detect it, the machine doesn't blue screen. You strongly encourage people driver writers, if they've got a class of device that fits into that, to leverage that. And the thing is, with both of those, KMDF and UMDF, that's a place where we're making sure that they work across XP all the way to Win 7.
Excellent.
So it's not like you're locking yourself into Win 7 if you're taking advantage of that. I wanted to mention one more thing about the performance and battery life, and that is something that when we look at the way that the system operates, there's lots of system services, both in Windows and from third parties. And a system service, by default, starts when the system boots. Early during the login process. Usually, if you boot the machine, you log in, the services are starting up, and we introduced something in Vista called delayed auto start, which puts a delay on when the service actually launches, so to get out of the hot path of you wanting to get to Outlook when you're logging in. But rather than starting them at all, there's many cases where we say, well, this service wants to start, but only if this condition's true, only if the machine's IP address changes, only if group policies come down to the machine and the service needs to do something about it, only if a certain device has come online. And so now we've got this thing called triggered started services in Win 7, where you can configure a service to only start up on a particular event. You can even have them start up on a custom event defined by ETW. So you can say, start up whenever this ETW event fires, because my service needs to do some response to that. You could also say, wake me up when the system loses an IP address because I need to do something. And so we've taken a whole bunch of services in Win 7 and made them trigger started, and that's going to be an API that we're going to encourage third-party service developers to go take advantage of.
Outstanding. Well. So one of the things that I always found to be incredibly interesting, based on I bring this interview up every time I talk to you, and I really want to do this interview again. I want to get all you big brain architects a part of CoreArch and have a conversation.
Yeah.
Because one of the things I loved about that conversation of a few years ago was the notion of detangling the Windows mess, or the operating system mess. So what I'm really curious, I know you did a lot of work in Vista to sort of rip things apart and try to get an understanding of the system as a whole. You have that huge map of dependencies. In Windows 7, I'm sure that work has continued. Can we talk a little bit about that?
Well, in interviews before with you, I've talked about something called MinWin.
Yes.
And there's been, even despite that interview being out there, I still see a lot of confusion out there about what's the difference between MinWin and server core.
Really?
Yeah.
Okay.
And embedded Windows. And so let me try to explain it one more time.
Now listen this time, people.
So I've come up with another analogy.
Okay.
Server core is like taking Windows and taking scissors and just cutting out the bottom of it. And saying, okay, this is what we think we need to run these server roles. So we'll call this server core, and we'll test these roles on this bottom part of Windows, and yeah, it looks like it works. We've got test cases that are supposedly exercising every functional path through the server role, and it looks like it works. Despite the fact that there's lots of threads. Basically, when you cut, it's a very not unclean operation from the perspective of you've got threads or dependencies that are dangling. So there's some piece in what you've got left in server core that if you called this function, it would try to call something that's not there, and it would fail. And we don't even understand, the system is so complex, really all the paths through that would fail. So that's why we say server roles need these APIs. We're going to make sure that those work inside and are contained, but we have no guarantee if you take an arbitrary app if it's going to run on server core or not, because we just don't know ahead of time what APIs is going to call that might go through some path that might end up falling out the top of server core. So and each time, WinPE is kind of like that too, if you're familiar with Windows pre-installation environment, which is part of the OPK, the OEM pre-installation toolkit. That WinPE, you take all of Windows and you cut out a bottom part of it, and you say that's enough to run the kinds of things that people seem to want to run on top of WinPE. So we'll call that. Now, as Windows evolves and components come and go and change and get moved, and new APIs come and go, there's no way for us to know how that's affecting server core or WinPE. I mean, the next time we release server core for Server 2008 R2, it's the same exercise. Let's go make sure that we didn't break server core, those roles. And we might have to move that, take all of Windows again and cut the line someplace slightly different. And that's just not a sustainable way to make, to have testing and engineering, agility. And so MinWin, which I explained before, is a different approach to that problem, and that is analyzing the dependencies of the system, making that giant graph you talked about. So there was a giant dependency graph where components were placed in different layers in a layer hierarchy based on who calls them, right? And we try to put things lower in the map if they get called so that they're called from pieces higher in the map, and then it makes sense from a layering perspective that if you got something at layer 2, it's not called from something from layer 1, it's called from things at layer 3 and above.
Okay.
And then we said, okay, so the bottommost part of Windows that we want to be able to carve out and build separately from the rest of Windows, and we want to be able to boot it so that we can test it, where in that map should we draw that line? And so Rich Nez and Rich Pletcher, really the guys that did this analysis, and then took a look at that map, looked at where that functionality that they wanted to be able to have that testing component that they could boot, and said, okay, it's right here. Looks like the line's right here. Now what they found is that there's lines, or dependency lines, where something in layer 2 calls down this, or layer 15 calls down to something in layer 14, which ends up calling up to something in layer 17 and saying, well, that's not good. We can't have something calling out of this because then it's not fully isolated. So then they go and move APIs around so that now where MinWin is, there's no lines out, there's no threads, because we've moved APIs around. And so that the layer at where MinWin is defined is clean with respect to the rest of Windows outside of that. And now we've got that thing isolated in the build tree, so we can build it separately from Windows, we can boot it, we can test it. We've got working on having our test suites be able to run on top of MinWin. So now, because there's no dependencies out of MinWin, we can innovate inside of MinWin, the pieces in MinWin, which I call Cutler's NT, because it's really the Windows NT kernel, the executive subsystems, the memory manager, the plug-and-play manager, actually not plug-and-play. Plug-and-play's outside of MinWin. But networking is in there because we want to be able to hit this thing from the network. File system drivers you can choose to put in MinWin. Okay. So you can boot MinWin off a file system and test it. And with that, when we innovate at that inside of MinWin, we're not affecting anything outside. We're not taking dependencies or needing to modify things outside of MinWin.
Awesome.
So tremendous amount of work, and there's a lot more work to be done, because now that we've got that, it's looking at the next level. Where do we want to draw that next line, and continue doing this work of cleaning the system and making it into nice, composable, testable, self-contained pieces.
Outstanding, and that's huge.
Yeah.
Because then you can make an innovation in the shell, for example, and not have to rebuild the whole system.
Exactly. That's
And you
that's
can
that's
deliver
what-
the shell
that's
over
kinda
the
your
service.
You've jumped right to the kind of one of the
Yeah.
end games, yeah. But that's where we want to go.
That's awesome.
Yeah.
So again, just so people get this straight, because I've heard Microsoft people make a mistake as well. MinWin is basically sort of an enhanced kernel, right? Contains all the important.
It's not enhanced. It's just a bottommost part of Windows, right? It's about 40 meg on or 30 meg on disk, 25 meg on disk,
Nice.
and versus server core, which is like 1.2 gig on disk. So you can see it's not a whole lot, but it's enough for us to make that first step and get that engineering unit isolated and understand the process by which we go about doing that. The way this is visible in Windows 7 is that there's new DLLs now. There's like kernel base. So kernel 32 is one of these DLLs that needed to be refactored, we call it. So some parts of kernel 32's API implementation didn't belong in MinWin and some parts did. So how do we address that from an app compat perspective is that we legacy apps call functions in kernel 32. Some of those now live inside of MinWin, some of those don't. And we've got forwarders now from the pieces that to the APIs that live in MinWin. Those are now exported by kernelbase.dll. So really you can think of it as kernel 32 is layered now on top of kernel base. And if you're writing something which nobody outside of the kernel team would write, but if you're writing something that's going to be calling a function in MinWin, you'd be calling kernel base functions, not kernel 32 functions. Even though you could call kernel 32, it would still work. From an engineering perspective, inside of MinWin, you need to call kernel base, not kernel 32. Right.
Very cool. So I mean, just to be clear, so Arun, the genius who broke apart the Spinlock dispatcher, he didn't have to rebuild all of Windows to test his code. He could just rebuild MinWin, right?
He could have done it. I don't think he.
Oh, you don't think he did?
Yeah.
Oh, okay.
Because he wanted to run bigger. We didn't have it ready for testing on the scale that he needed to test it on. I mean, when you do something like break apart the dispatcher lock and want to make sure you got it right, you want to
make sure you have the whole system.
Yeah.
Fair enough.
Yeah.
So excellent. So I think Windows 7. Even I get it now. I mean, MinWin. I think it's clear. And before we end, I mean,
well, there's a couple more things.
Yeah, that's what I'm saying.
That were worth,
Please.
Worth bringing up that I think are pretty cool, and these are really in the virtualization space.
Cool.
So, and kind of indirectly related to virtualization, kind of management at an enterprise level, and where we're going with being able to manage Windows and separate the distinction, the hard distinction that we've been blurring over time of what is a physical machine and what's a virtual machine. We want to continue to go down that path, and that means when you have a Windows system, it'd be nice to not have to say whether it's physical or virtual, but just to be able to say when you're provisioning this thing in your enterprise, well, maybe it's virtual right now. It's running on a machine with other Windows VMs. But at some point, I want to, because of the workload changed, I want to move this thing off into a physical machine. Or I want to create libraries of Windows images and then just be able to put them, reference them from client machines or copy them down to client machines and just boot them, not have to get them ready to run. So what we got now is a couple things: the ability to mount a VHD natively within Windows. So previously you'd have to use a tool, the VHD mount tool, which was part of Virtual Server 2005, or came with that. And so now that we've got DiskPart, the utility that's built into Windows, now you can use that to mount a VHD and to create VHDs. So that's part of showing how we're making VHDs first-class citizens in Windows. And the other is we now have the ability to boot Windows directly from a VHD. So you can have a Windows in a VHD image, and you change the boot configuration database to point at that VHD, and now you can boot Windows right off of VHD.
Nice.
So, I mean, I think that's a really cool thing. I gave an internal presentation at our internal kind of version of Tech Ready, and I did the whole thing off of Windows booted from a VHD, running PowerPoint, and at the end I showed them how I'm doing that.
Very cool.
And that means that required having a driver that understands the VHD format running inside of Windows. It's kind of a bizarre thing because you end up going through NTFS into the VHD driver, which looks like a storage device, and it figures out where the thing is really on the real disk, and then you come back out and go back into NTFS and go down to the real disk. So it's interesting issues regarding device arrival and removal, how you shut down file systems and volumes in the right order.
Yeah.
A bunch of things that had to be worked out there, but
And you worked it out.
yeah, worked it out.
Nice.
Yeah.
Very cool. What else?
I think we've covered the list. I mean, there's been things like registry, some enhancements in the registry to improve performance and scalability of registry operations. One of the things that was done in, I think it was Windows XP, is the registry moved from paged pool, which is a kernel virtual memory that's backed by the paging file, to being a memory map, treated as a memory map file, where when you reference the registry in XP and Server 2003 and Vista, you're actually referencing the file on disk, the bits on disk, and just mapping views into that disk, that file image. Well, when Win 7 we've gone back to the putting in the paging, back in that paged pool, and that's had some scalability improvements, which now that we've got dynamic address space, which we introduced in Vista, that was kind of before that there was a limit on, kind of artificial limit on paged pool, and that's gone. Now we've got 64-bit systems, and so that made it right time to go back and do that.
Very cool. Now, one of the things I think, like if you think about, some people are of the perspective, for example, in the case of programming languages, as programming languages evolve, some people think it's better to take things out, not put new things in. So, have you taken things out of Windows 7 that through telemetry we saw weren't being used, weren't being utilized, weren't necessary?
We might have, not that I'm aware of though. And I mean, one of the things is we've realized post Vista that if we want to remove something, we need to put telemetry into this to see if we can remove it first, because we're now being ultra cautious about things. So there might be a handful of very minor things that we've removed, but one of the things is if there's any risk of us breaking something, then, and you think you're like, well, I don't think anybody's using this, or anybody that we can't go talk to fix their code, some lightweight ISV that's updating their code frequently and everybody's getting updates, then we need to make sure that nobody's using it really before we do that, and that means putting in SQUIM data collection, which is when on a sampling of computers where people opt in to the customer experience program, then we're monitoring in a way that ideally doesn't get in their way at all, they don't notice, by sampling, right? How often these things get called, and then we can send that back up and we can see, well, actually it looks like on that sample population we've got, which ends up being hundreds of thousands and millions of machines, that we don't see any apps calling this API, so the risk of us removing this API is small. So there's a bunch of things in Win 7 that are instrumented this way, so that we can go look at that as Win 7 goes out, and then in Windows 8 saying, well, nobody's calling those, let's get rid of them.
Outstanding. And you, of course, are already thinking about Windows 8, probably Windows 9, 10,
Not
11.
supposed to say that.
No, there's not supposed to say that. I mean, you're, as a technical fellow on Windows, you are tasked with, you have to think way out.
Yeah.
It's not that you don't pay attention to what's here. I mean, you have to, you have a whole team, people that are implementing this stuff.
Yeah. A lot of things in our roadmaps. I mean, you see the multi-core stuff is a trajectory in the future, the virtualization stuff. I didn't mention extended page table and nested page table support, which now we've got coming in Hypervisor V2, which is coming out of Server 2008 R2.
Nice.
That is taking advantage of hardware memory management support that Intel and AMD have been working on. So we got that. I mean, but we've got a roadmap of a whole bunch of things, that are going to keep us busy for a while.
Outstanding. So, thank you for your great work, and thanks for coming on Channel 9 and spending some time with us.
It's always fun.
All right, we'll see you soon.
All right.
Bye.